Okay. So let me try this. And so I had been talking about the Muirhead inequality and Richard Rado's very beautiful generalization of it. And it led to a paper of Sundarajan on a question about Egyptian fractions. So that's what I want to talk a little bit about today. It's always nice to go back to the source. So I will draw your attention to the following book. Let me see if I can go to this document camera. There we go. So many of you might be familiar with Otto Neugebauer, who was both a serious research mathematician and one of the great historians of mathematics. And so there's this very famous book on mathematical texts, and so here they are. If you want to see Egyptian fractions, here they are. And occasionally when I've taught the history of mathematics, it actually takes about 15 minutes to learn the hieroglyphics of numbers. So you can actually, with a magnifying glass, read these things. And it's interesting. Anyway, if they say go back to the sources or read the original papers, here they are. Yeah.
I've got this. This is USB-C.
Okay. If you want to get a little bit more modern, so let's see, what can I say? Not everyone knows about Egyptian fractions. There is a remarkably humongous literature on this subject. And if you look at the most recent papers, you see the name of Christian Elschultz appearing a very large number of times. So an Egyptian fraction is just a unit fraction, something of the form 1 over x, x a positive integer. And we're interested in the question of writing some rational number between 0 and 1 as a sum of unit fractions. And Fibonacci made the following observation. The greedy algorithm always works. So what that means is, given, let's just say, let's call it theta maybe. Well, given A over B, choose x, the smallest positive integer, such that 1 over x is less than or equal to A over B is less than 1 over x minus 1. So 1 over x is the largest Egyptian number you can pick, less than or equal to A over B. And you let A over B be equal to, let's call this x1, 1 over x1 plus whatever the remainder is. So, and then you continue this process with the number A over B minus 1 over x1. So you'll get the largest Egyptian number you can, which is less than or equal to a over b minus 1 over x1. And of course, you need to know that this really is an algorithm that terminates in a finite number of steps. So you just make the following observation.
I'm in Zoom.
If you have 1
How
over
do I
x,
just get this screen?
oops, let me,
Let me get this screen.
Just that screen.
try and mute people if I can. 1 over x less than a over b, less than 1 over x minus 1. Let's see if I can do arithmetic. It's not always the case. A over b minus 1 over x. This difference, this is what? Ax minus b over bx. And according to this, ax minus b, oops, let's see if I can do this. B is less than or equal to ax. So ax minus b is greater than or equal to 0. And ax minus b is less than a. So I have my fraction a over b. I choose the largest unit fraction 1 over x that's less than or equal to a over b, and then I look at the difference. And the difference is again a fraction. This might not be reduced to lowest terms, but in any case, ax minus b is strictly smaller than a. So as you go through this algorithm of picking successively the largest Egyptian numbers you can, the remainders have the decreasing sequence of numerators, positive integers decreasing. At some point, it has to stop. Since there's some principle they teach you in preschool that a strictly decreasing sequence of positive integers has to be finite. So this is Fibonacci's algorithm. And it's very nice. Now, Sylvester, again, no one knows who's the first to do any of this, but I'll come back to Sylvester. I want to explain how one gets from Muirhead's inequality, whatever that is, if you missed the last couple of talks, to Egyptian fractions. So I'm going to try an experiment. My experiment is to try to avoid writing stuff. So let me try if I can share the screen with this. So is this paper visible?
Yes.
Yes, okay. And I can try to make it bigger if I can. Maybe I don't know how much that helps. So, because Muirhead's inequality requires a lot of writing. And let me just state the inequality and then specialize it in a couple of ways. So A is an n-dimensional vector with non-negative coefficients, non-negative coordinates. And X is going to be a vector with strictly positive coordinates. The coordinates are real numbers. They don't have to be integers. And associated with this vector X and this vector A, we have the monomial x1 to the a1, x2, and so forth. And this is just a number, right? So it's just a number. And what Muirhead did is he averaged out the value of these monomials over all possible permutations of x1 up to xn. So what you might call, if you like, excessively syllabic names, the Muirhead monomial symmetrization function, this M from Muirhead, you take over every permutation in Sn in the symmetry group, x1, x sigma 1 up to sigma n, you look at this monomial, but where you've permuted the x's in all possible ways, and you take the average. Of course, this product, I going from 1 up to n, x sigma I to the power ai is exactly xi to the power a sub sigma inverse of I. So if you want to have your permutation appearing in the exponent instead of as the subscript of the variable, this is just a way to do it. And of course, if you sum over all permutation, all elements of a group, it's exactly the same as summing over all the inverses of the group. So if you don't want to carry these minus ones around, you can just write it like this. And so this is this expression. Now, if you evaluate this at the particular following positive vector, so let x1 be E, and all the other coordinates in the x is equal to 1. So when you raise 1 to a power, you just get 1. So in this sum and product, this product is just x1 to the a sub sigma of 1, right? All the other terms disappear. And for any given I, how many permutation sigmas send 1 to I? N minus 1 factorial of them. So this is really n minus 1 factorial over n factorial times just the sum of e to the ai, or 1 over n times this. So when I evaluate this function at this particular vector, I get this. Now, what does Muirhead's inequality say? It says if you take two non-negative vectors, a and b, and a majorizes b. So in Hardy, Littlewood, and Polya, the definition of majorization, which is the standard definition, has to do with the fact that if you write these, if you permute the coordinates of these vectors, so they're in decreasing order, that the partial products of the b's are less than or equal to the partial products of the a's. And the equivalent geometric condition, which as far as I know was discovered by Rado, is that that's exactly the same as saying, if you take the polytope generated by all the n factorial permutations of these coordinates, that the vector b is in that convex polytope. So either algebraically or geometrically, you have this notion of the vector a majorizing b. And Muirhead's inequality says that if you take a vector x, which is not a constant vector, so there's some p and q where the coordinates xp and xq aren't the same, then if you symmetrize with respect to the exponent vector b, and you symmetrize with respect to the vector a, if a majorizes b, then this number is strictly greater than this number. Okay. So in particular, if a majorizes b, this sum is bigger than this sum. I can just get rid of the ends. I have this nice inequality. Okay. So this is a very, very, very special case of Muirhead. And we can specialize it a little bit more as follows. If I take n numbers ui and vi, all bigger than 1, and I let ai and bi be their logarithms. So if these numbers are bigger than 1, the logs are strictly positive. Just positive is enough, or non-negative, but they're positive in any case. So I have these two positive vectors. And if so from the vectors u and v, I get vectors a and b. Like the coordinates of a are the logs of the u's, and the coordinates of the b's are the logs of the v's. So when I do that, if a majorizes b, well, what does that mean? So a majorizes b means that the partial sums of the v's of the b's are less than or equal to the partial sums of the a's, which means the sum of this logarithm is less than this sum of logarithms, or the log of this product is less than this. And similarly for when you have equality of the partial sums. So if you take the numbers ui and vi bigger than 1, and we let a and, well, bigger than 1, and you look at these vectors, these positive vectors, that a majorizes b, if and only if you now have a condition involving products and not sums. The partial products of the u's are greater than the partial products of the v's for k going from 1 up to n minus 1. And when you take all n numbers, the products are equal. So if you now apply, so if A majorizes B, which means these multiplication conditions are satisfied, Muirhead's inequality says this sum is less than this sum, but the A's and the B's are the logs of U and V respectively. So you get some relationship, some inequality about sums. So let me just write that all down. Oh, sorry. Let me do one more thing. What I just stated was in the case when the U's and V's are strictly greater than 1. Suppose you have positive numbers U and V, but they're not necessarily greater than 1. All you know is they're greater than 0. So if you take any lambda that's positive, and you can choose a lambda large enough that lambda UI and lambda VI, all of these numbers are bigger than 1, then this condition on the partial products holds if and only if when you multiply by lambda, it still holds. And this condition on the product holds if and only if the condition when you multiply the U's and the V's by lambda holds. And similarly, our conclusion that this inequality obtains, that's true if and only if this is true. So when you put that all together, we have the following kind of corollary of Muirhead. And what's interesting is it says absolutely nothing about the symmetric group, about monomials, about symmetrization. It says the following. If you take positive numbers, U1 up to UN and V1 up to Vn, if the partial products of the first n minus 1, well, k going from 1 to n minus 1, if you have this inequality of the partial products and equality for all the numbers, you have this inequality. Okay. Now, I'm rather curious. I don't know. I mean, this is, as they say, this is in the literature. You can find it written down, but the only place I've seen it written down is using Muirhead's inequality. And I'd be rather curious to know whether there's a direct proof of this. Even if n is a small number like 3, it's not so obvious what to do. So in this theorem, the U's and the V's are positive. This condition on the partial product, this partial product inequality is satisfied, but we have equality when we take all n of the numbers together. I want to get rid of this condition. I like this to be less than or equal to. So in fact, you can do the following little trick, which is the following. So again, we take n positive numbers, U1 up to UN, and n positive numbers, V1 up to Vn, and we assume this condition on the partial product holds for all k from 1 up to n. In particular, when k is equal to n, we don't assume equality here, it's just inequality. But the same conclusion holds, I claim. And we do that by using the following, if you like, the following little trick. Take any number you like, v sub n plus 1, and divide, so it's positive, and divide un plus 1 like this. So this is positive and this is positive. And this ratio is at most 1. This is by this inequality. So Vn plus 1 is at least as large as Un plus 1. But now the way I define this, the way I've constructed the Vn plus 1 and the Un plus 1, if I look at the n plus 1 numbers, the U's and the V's, this n plus 1-fold product gives me inequality. So therefore, I have an inequality for the sum of these n plus 1 numbers. But the sum of just the first n numbers is then less than or equal to, this is the sum of the first n plus n numbers, plus Un plus 1 minus Vn plus 1. And the Vn is greater than or equal to the Un. So this is something non-negative. So this is less than this. And by this sort of stupid trick, I have a slightly improved inequality. And again, this has nothing to do in its statement with symmetrization or it's just an inequality about positive real numbers. And I would be interested if there's a independent proof of that. Okay, so keep that inequality in mind. We're going to come back to it. And we come to Sylvester, who wrote a paper on vulgar fractions, which I sent out with the announcement of this talk today, because it's a great paper and nice to look at papers, old papers. So Sylvester's sequence is the following sequence of positive integers. It's constructed recursively as follows. A1 is equal to 2. And if you have A1 up to AN, you get AN plus 1 by taking the product of the first n numbers and adding 1. So the numbers go 2, 3, 7. They get big very, 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 very quickly. And in the online encyclopedia of integer sequences, it is sequence A 000058. That's the sequence. And it has a lot of very beautiful arithmetical properties. If you take the sum of the reciprocals of the first n Sylvester numbers. By the way, let me just go back for 1 second. If you look at this recursion, this is exactly Euclid's proof that there are infinitely many primes. Because if you start with A1 up to AN, you multiply them together and add 1, you get a number. And this number, which is bigger than 1, is relatively prime to each of these integers. So all the prime factors of AN plus 1 are different from the prime factors of any of the previously constructed A's. So this is what Euclid did. It's very nice. So if you take the sum of the reciprocals of the first n Sylvester numbers, it's always less than 1. And 1 minus that is exactly 1 over the product of all the numbers. And among other things, the Sylvester numbers satisfy this nice formula. You don't have to multiply things a lot. You get from AN to the AN plus 1 just by x squared minus x plus 1. That's the formula that gives you AN plus 1 from AN. And it's just a straightforward kind of calculation to check these two things. Now, there's another way to get Sylvester's sequence, and that's the following. For every n, always let AN be the smallest integer, which means the fraction 1 over AN is the largest Egyptian number, such that the sum of these n Egyptian fractions is strictly less than 1. So this is an under approximation of 1 by Egyptian fractions. So you always, and you're using the greedy algorithm, but not exactly Fibonacci's greedy algorithm, or maybe it is exactly Fibonacci's greedy algorithm, but you never want to hit your number. You never want to get to 1. So of course, what's the largest Egyptian fraction less than 1? It's a half. So the first number you pick, A1, is 2, which is the first term in Sylvester's sequence. Now, suppose this is just by induction. Suppose you've constructed the first n numbers in this way. Like to see, what would the next number be? You want to get, you want to find the largest Egyptian number such that 1/2 plus that number is less than 1. It can't be a half plus a half, because that would equal 1. But a half plus a third, that works. So the next number in the sequence, the next Egyptian number would be a third, and A2 would be 3, which is the second term in Sylvester's sequence. So suppose that the first n terms you've constructed are in fact the first n terms in Sylvester's sequence, and so by the lemma on the previous page, previous slide, if I take 1 minus the sum of the reciprocals of the first n Sylvester numbers, that's exactly equal to this Egyptian fraction, 1 over this product. So the smallest Egyptian, the largest Egyptian fraction, the smallest denominator of an Egyptian fraction, which is strictly less than this, is the Egyptian fraction whose denominator is this product plus 1. Okay. So if 1 over an plus 1 is the largest Egyptian fraction, or the fraction with the smallest denominator that satisfies this inequality, it's exactly the product of the first n a's plus 1, which is the n plus first term in Sylvester's sequence. So Sylvester's sequence is constructed in this way. Okay, now exactly 100 years ago, was 100 years ago, 1921, in a note in the monthly, a mathematician at Harvard named Kellogg wrote a little paper, and he said, I proved something, but I never wrote down the proof, but I mentioned it somewhere in a letter or a lecture. And Carmichael told me he thought it was really very interesting. So I tried to write down the proof, and I realized I couldn't remember my proof, or maybe I never had a proof. And he then proceeded to write a paper about the fact that he didn't have a proof of his statement. A year later, another mathematician named Curtis from Northwestern published a paper in the monthly in which he said he proved Kellogg's conjecture, Kellogg's statement. And in their book on old and new results in combinatorial number theory, Erdős and Graham mentioned the theorem, and they say it was often rediscovered, but it was first proved by Curtis. In his paper, Curtis says he actually Curtis puts a statement in his paper that is kind of like a note added in proof, that he just received a paper from a Japanese mathematician named Takenouchi, in which he also proved the same result. And I included that paper in the email announcement I sent out this morning, because it's a very good paper. And again, it's not well known at all, I think. But as you look around on the internet for what is going on and connected to what came up was some email correspondence between Jerry Meyerson and a guy named Bartels, in which Bartels started off by saying that Curtis's proof was wrong. And then there was some further email correspondence. And then Bartels wrote something like, actually, Curtis's proof is okay. It's just hard to understand. And I've proven something. And so I truly don't know what in terms of like the history of the subject, I don't know what who might be said to have first proved this. I assume it was actually Takenouchi, because his paper looks very good and it's much easier to read. So what is the statement? So we just saw that taking the sum of the reciprocals of the first n Sylvester numbers gives you an under approximation to 1. And I'll call it Kellogg's conjecture, is if you take any sum of the same number n of Egyptian fractions, and if the sum of the 1 over b's is still an under approximation to 1, but greater than or equal to the summation 1 over a, in fact, ai, and the b's are in increasing order, then ai equals bi for all I. That is, if you're going to use n Egyptian fractions, the closest you can come to 1 and not be equal to 1 is taking the first n terms of Sylvester's sequence. And Soundararajan posted some time ago, a long time ago, on Archive, a proof of this using Muirhead's inequality. And he never published it, but I asked him if he had published it. He said no, but he sent me a list of papers that have been published. You know, you go to Google Scholar, and you put in a paper and you see who has referenced it. There was a very long list of papers that they didn't use Soundararajan's proof or method at all. They used this theorem and they just cited Soundararajan for the result. But the proof is very beautiful, and I want to show it. And it generalizes in a lot of ways. But let's just look at the proof of the simplest statement, which is Kellogg's conjecture, a theorem of many people, let us say.
Are you using, Mel, are you using essentially Takanushi's proof or?
No. I'm using Sound's proof. I'm using the inequality. Let's see, let me just go back for a second. So I'm using this inequality. If you take n positive numbers, u1 up to un, and n positive, oops, let me go back, more general form. N positive numbers u1 up to un, and n positive numbers v1 up to vn. And if the partial products of the first kv's is always less than or equal to the partial products of the first ku's, then the sum of the v's is less than the sum of the u's. I mean, so this doesn't look like Muirhead's inequality, but it's a corollary of it, if you like. That is, I use Muirhead's inequality to get this. And this is what Sound uses. And the proof is going to be by induction on n. So of course, if n equals 1, the first Sylvester number is a half. And if you have one, that's all nice. Here we go. So suppose n is 1. So you have 1 over a1 less than or equal to 1 over b1 less than 1, but a1 is 2. And 1 over b1, it's at least a half and less than 1. So that means b1 has to be equal to 2. So b1, so in the case n equal 1, b1 must be the first Sylvester number. Okay, so let n be at least 2, and let's assume that this theorem is true for whenever you have strictly less than n Egyptian fractions here. Okay, now, so 1 minus the sum of the b's, a common denominator, not the least common denominator, but a common denominator of these n integers is their product. So this is some fraction. You can write this as a fraction r with this denominator, and this fraction is positive, right? 1 minus 1 over b1 is greater than 0. So the smallest fraction with this denominator is 1 over the product of the b sub i's, all right? So that's observation number 1. But we also showed when A is the Sylvester sequence, that 1 minus the sum of the first n a's is exactly equal to 1 over the product of the first n Sylvester numbers. So I have that this 1 over the product of the a's, which is 1 minus the sum of the reciprocals of the a's, which is greater than or equal to 1 minus the sum of the reciprocal of the b's, that's this inequality, which is at least 1 over the product of the b's. So they teach you somewhere that if a fraction is smaller than another of this form, this denominator is bigger. So the product of the b's is bigger than the product of the a's. Okay, the product of the b's is bigger than the product of the a's. Now, suppose I let m be the largest integer. So like the tail of the product of the A's is less than or equal to the tail of the product of the B's. So M is the, I mean, M could be 0. It might be that this is true for I equal 1 to N, but it's not true for any larger. You can't go for like from 2 to N or 3 to N. You have the inequality would be reversed. So you let M be the largest integer such that this product of the last N minus M terms of the A's is less than or equal to the last N minus M terms of the B's. Now, the induction hypothesis says if you have M less than N, right? M has to be less than N, that the sum of the reciprocal of the first M A's is at least the sum of the reciprocal of the first M B's, because this is less than 1, and for M less than N, the Kellogg conjecture is presumed to be true. So for the first M numbers, we have this inequality. Now, so the product from M plus 1 to N of the A's is less than the product from M plus 1 to N of the B's. Now, if in fact you had an inequality from M plus 1 up to some M plus K, where K is between 1 and N minus M, then, so this is, I mean, this is all just, you know, preschool math, if you like. The product of the A's from K plus 1 up to N is less than the product of all the B's, that's this times this, divided by the product of the A's from M plus 1 to M plus K. And this product, we said we're assuming that if this inequality holds, this is less than or equal to 1. So we would have this inequality, which is absurd because M plus 1 is the smallest integer for which an inequality of this form, M plus 1 is the smallest integer for which an inequality of this form holds. So for all K from 1 to N minus M, we have this partial product inequality. But this is exactly the hypothesis, what we needed to apply our inequality, that if you have the partial products, if the sequence of partial products of the A's is less than the sequence of the partial products of the B's, then the sum of the A's is less than the sum of the B's. Well, that's true. Of course, it's sort of in the wrong direction. So let me just take reciprocals, right? Just, you know, if this is true, the product of the reciprocal of the A's is greater than the product of the reciprocal of the B's, right? That's what I'm saying. And from this, by the corollary to the Muirhead inequality, we get this. So we have this from M plus 1 to N. We already had it from 1 to N. So we have this from 1. So this is what we wanted to prove. Right? You can't do better, you know, in an under approximation of 1 as a sum of N Egyptian fractions than by choosing Sylvester's sequence. Right? That's the proof. Now, okay. So that's a real proof. So not the proof Kellogg had, almost certainly. Well, we don't know what Kellogg had. It certainly is different from what either Curtis or Takenouchi did, but it is a very lovely proof. So let's see, let me try something else. Let me stop share for the moment. So this suggests an infinite number of questions, of course, because there are a lot of numbers. And so what we might call the Kellogg XYZ theorem, you put in whatever name you like there, is that if that it says basically Fibonacci's, you might call it under approximation algorithm gives the best Egyptian fraction under approximation for theta equal to 1. And is this true for all theta positive between 0 and 1? If not, for what theta is it true? Well, the answer to the first question is no. And here is a simple example. Let me just come back to this because I wrote it out. Here. Suppose I take a number theta in strictly greater than 9/20 and less than 11/24. So this is an interval of length 1/120, if you're curious. So there are a lot of numbers in that interval. And if you take any number theta in this interval, rational or irrational, it doesn't matter, we can make the following observation. First of all, a third is less than 9/20, is less than theta, is less than or equal to 11/24, which is less than a half. So if you pick the largest Egyptian fraction less than 9/20, it's a third. And then you subtract a third from theta, and you get what? You get that's less than or equal to an eighth, but greater than 9/20 minus a third, which is 7/60, which is greater than a ninth. So if you take the largest Egyptian fraction less than theta minus a third, that's a ninth. So that's what your A2 is. So a third plus a ninth is less than theta, but a third plus a ninth is actually less than a fourth plus a fifth, which is 9/20. See, this is 4/9. And 80 is less than 81. So this is correct. So for any theta in this interval, the greedy algorithm gives you a third plus a ninth, but a fourth plus a fifth is a better under approximation of length 2. Right? So the answer to this question, does this greedy algorithm always give you the best under approximation? The answer to that question is no. And then you might ask, for what theta is it true? So as far as I know, this problem in its generality is unsolved. So there are various results. I mean, I have some, but I have no idea what, I mean, because this is all sort of new to me, and everyone knows it's, you know, there's this saying about academics that everybody writes, nobody reads. So it's easier to prove a theorem than to spend a lot of time going through the literature and trying to track down what's known. So, for example, it is true for Egyptian fractions. If you take theta equal to 1/q, the greedy algorithm always gives you the best under approximation. And there are a number of other results. In fact, in the Takanuchi paper, he has some results about certain fractions A/B. But as far as I know, the complete list isn't known. This really is an interesting question. Now, there's another question, which is interesting if you like. and this is one of the things I guess I had considered in the one paper I had previously written, but this is just a special case of that. Suppose we sort of extend the set of Egyptian fractions 1 over n, and in positive integers, to fractions of the form, let's say, I don't know, you never can pick a good letter, r over n, where n is an integer, a positive integer, and r is in some finite set. Let's just say maybe just r are all the numbers, r is in the set of all numbers from 1 up to capital R. So now in our approximations, I say maybe just 1 and 2. So suppose we consider fractions 1 over n, 2 over n. And again, we can apply a greedy algorithm, it's certainly going to always terminate, to represent every rational number between 0 and 1 as a sum of like 1 over n or 2 over n. You can prove, I mean, this hardly deserves the name of the theorem, in the Fibonacci algorithm, that is the greedy algorithm, if you write a over b, or if you write some theta as summation ri over xi, I guess, ri over ai, the ri is equal to 2 for all I. That is, you always actually end up with 2's there. And that's true if you take any finite set of numerators. It's always the largest one that will appear. And again, it's interesting to try and see in what cases something analogous to the Kellogg conjecture holds. So, I mean, there are a number of results about this, which I would have talked about today, in fact, but I stopped writing when I got to here because it was 2:30 and people were logging on. All right, until I got to that those notes I had written out. But all these questions are open. That's the whole point. I mean, it's really interesting. And I guess that's really all I want to say today. So I am happy for comments or questions. And I would also ask Christian, who is the local expert on this, whether he's seen, things like this before or knows of any results about this, or anyone else who might have some knowledge on this. In the Richard Guy, I'm sorry, go ahead.
I have a question, Mel.
Sure.
One of the most beautiful things about the Fibonacci sequence is the Lamet's proof of the complexity of the Euclidean algorithm. Is there something related to the Fibonacci algorithm that's one has its complexity been analyzed anywhere? Or, I mean, it's...
Yes. I believe there is also a large literature on this question. So if you just do the very simple, if you make the very simple observation I did, which is in each step of the Fibonacci algorithm, the numerator of the remainder is strictly smaller than the numerator of its predecessor. So if you start with the fraction a over b, the algorithm terminates in at most a steps. Now, I might even have it here. Lord. somewhere in or around my desk in one of the many, oh, here, maybe it's here. Let me just check. I think there's some reference to estimates in the Erdős-Graham survey.
All right.
And you get something like log A or log B or maybe log. I know I've seen this recently.
All right. Yeah, I have another question.
But in any case, the answer is people have certainly looked at this. That's really all I can say.
All right. Yeah, the other thing is the question of the length of the representation of a rational number in terms of Egyptian fractions. If one looks at sequences like the, let me see, just some natural sequence. If anyone has looked at the length of the representations, let's say using a particular algorithm, like let's say I look at let's say a sequence of primes, and I look at the fractions p minus 1 over p. If I want to represent that in terms of the Egyptian fractions, let's say using Fibonacci's algorithm, is there some information about the length of the fraction, the number of terms that will appear?
I'm sorry, could you repeat that?
Yeah, let's say I take a natural sequence, let's say just for the heck of it, the primes,
Okay.
and I look at the fractions p minus 1 divided by p.
Okay.
And I calculate things in terms of, I calculate the representation in terms of Egyptian fractions using a particular algorithm, let's say Fibonacci's algorithm. Does one know on the average what the length is?
Okay, so here's a partial answer to that. So there's a paper I mentioned in the last talk of Erdős. I mentioned it because I have no idea what's in it, because he wrote it in Hungarian.
Yeah.
And he says, so let n of AB be the least t such that you can write A over B as a sum of t Egyptian fractions.
Okay, yes.
Okay, so the maximum value, so fix your denominator, the maximum value of n of AB for A between 1 and B is less than log B over log B and greater than constant times log B, log B.
Oh, okay. All right. That's actually very nice. Yeah.
Right. But I mean, it's a huge gap. But
right. Now, one could probably make it more precise if you look at sequences like the Faraday fractions.
Right. But you know, also note this was proven 70 plus years ago. Yeah. And okay. The Erdős-Graham survey was written in 1980. So maybe in those 30 years, nothing was done, but it's still 40 years since this. And
right, yeah. I'll take a look.
This is very nice. And I have no idea how they, I literally looked at the paper, Sol was Hungarian, and that was it.
That could be Greek to me. Yeah.
Greek would be easier, probably.
Right. Okay. All right. Yeah, that's very nice.
Yeah.
Okay.
Anything else or comments, questions?
Yes, maybe a comment on the upper bound just of this, what you say, the upper bound by Erdős has been improved to square root of log B.
Oh.
Maybe 30 years ago, something by somebody called Vose, V-O-S-E.
Okay. All right. Yeah.
And do you have any idea how one proves an estimate on the running time of the algorithm?
I think an important ingredient of Vo's paper is he constructs a certain sequence with say quickly increasing sequence with say integers having a lot of small prime factors.
Okay.
Yeah. Actually, this I meant square root of log b, but then removing this log factor on the denominator.
Yeah.
Is that result best? Can he produce a sequence? It sounds like he could, that where you get the square root of log b.
Well, I would expect that square root of log b is still far away from the truth. I would guess that maybe it's log b to the epsilon. It's just nobody can prove it.
So you think log b might be I see.
Yeah, I would guess it must, the upper bound must be much smaller.
Has anyone done numerical studies?
Yeah, I don't know.
I mean, even yeah, I mean, in a sense, most fractions need a very small number, like closer to the lower bound, but
In terms of analyzing the complexity, it seems like we would also need to have some bound on x sub t, right? It's not great if we only need 10 terms, but one of those terms needs 10 to the 10 to the 10 digits.
Right. So that's actually related to the conjecture of Kellogg. He stated his result not the way I did in terms of under approximations, but as follows. If you write 1 as a sum of exactly n Egyptian fractions, where the denominators are increasing, and you can make them strictly increasing, then his statement was that the largest denominator that can appear is the nth Sylvester number, but minus 1, but that's essentially it. That may actually, so there's also the following somewhat mysterious statement. So this is an Erdős-Graham, I'll just call it a sentence. You can't call it a theorem because there's not a proof. You can't call it a conjecture because they didn't say we conjecture. They just wrote a sentence which says the following. They knew that, for example, 11 over 24 they knew that a third plus a ninth by the greedy algorithm gives you the best two-term Egyptian gives you the greedy algorithm applied twice gives you these two terms for 11 over 24, but they knew that 1/4 plus 1/5 is better. So just the greedy algorithm doesn't work. But they said, suppose we let Rn of theta be the n-term Egyptian fraction 1 over x1 up to 1 over xn less than theta, that is for n terms the best Egyptian fraction under approximation. I note, by the way, for Russell's benefit, that I'm hyphenating under approximation. We had a discussion about this earlier. So their statement is then for some n sufficiently large, the greedy algorithm applied to theta minus Rn of theta gives the best under approximation. So for example, for the number 11 over 24, the greedy algorithm doesn't give you the best under approximation for all n, it fails for n equal 2. But it might be if you take 11 over 24 minus a fourth plus a fifth, and you apply the greedy algorithm to this, from this point on, you always get the best under approximation. So this is like a sentence. They write this down. There's no reference, there's no proof, there's no, it's just, I don't know.
It was obvious to them.
An epiphany, all right? You know, the angel came down and whispered it in their ear. I have no idea. And as far as I'm aware, no one knows if this is true or not. For people who are interested, Christian Elschultz just put on in the chat a reference to the paper of Michael Vos on the algorithm, on the length of the shortest Egyptian fraction representation of the number. Huh? If anyone was parallel processing and watching the news during the talk, has anything come up for a vote in the Congress yet? Anyone know?
It won't affect universities, will it?
Well, it affects America, and what affects America affects American universities. So
Well,
it
let me
certainly
Proposing
affects
free
CUNY.
tuition for community colleges.
Yeah, that affects CUNY directly. But also many provisions of the reconciliation bill, you know, childcare, child tax credits, all that certainly affects many CUNY students.
Oh, 13 minutes ago, Congress passes bill to avert government shutdown.
Yeah, right.
Funding
That
bill.
they had worked out a deal for that. But that, yeah, that's good.
There's a picture of Pelosi here.
Oh, good.
The S&P took
Right?
a dive today.
Hey.
Okay.
By the way, it's very difficult to multitask when you're giving such complex proofs.
Right. I mean, it's easy for the speakers. Like, I'm convinced when I'm giving like my Zoom calculus class that 90% of the students have logged in. So in case I don't take attendance, but they might think that I do. So they log in and then they go off and do whatever they have to do for the next hour and a half.
There was a story about a teacher who caught a first grader. He figured out this trick. So he would log in and look attentive. And she wrote a note to his mother who caught him playing with his dog during class. And he had this attentive look on Zoom.
A prodigy.
Yeah, if he's that bright, why can't he? Yeah. I don't think it was a math class, so it wasn't that terrible a sin.
Well,
Right. Okay. Yeah, good to see you guys. Let me log out. So,
okay.
bye.
Let's see.
So Mel, you're going to put this on the archives eventually when it's polished and through, which it looks like it's becoming.
Hardly, but yeah, I will. I just, because really all I did today was give sounds proof and nothing of my own stuff that I, whatever the little bit I did. So, but yeah, I am trying to write this stuff up because otherwise it gets basically forgotten by me. Oh, I see still present is Ajmain Yamin. So I gather from your new email address that you are a graduate student at CUNY now. I mean, we had
Yep,
talked about that
that's
last
right.
year, but I didn't know what happened. So congratulations.
Thank you.
Are your classes being held in person?
No, the first year grad courses are all online.
So other than that sort of party they had in a park at just before classes started, have you met any of your fellow students?
So I'd have like regular meetings with one third-year student, and we're learning about automorphic forms. Other than that, not really.
Who's teaching the class on automorphic forms?
So it's a reading group, and it's supervised by Professor Gautam Chinta.
Okay. My thesis advisor did some work on automorphic forms. I think his wife's more interested in it. Harold Stark.
So do you think that no one knows if classes will be in person in the spring? But the thing, like at the colleges, of course, my building is simply closed because it's considered unsafe at the moment. They have to do something to the ventilation system, the math building, or the math physics building. But, and the problem is that a typical class with 35 students, if you're going to have social distancing, there's no classroom you can put them all in. But I assume that in the first year graduate courses, there are probably not more than 10 students in any given class. So at some point when they reopen the building, in principle, at least, it's possible for students to actually be in a classroom and still be 10 feet away from everybody.
Yes, some of the upper division courses, like intermediate level grad courses, are in person, but the first year ones are not in person. They're online.
Okay.
Where are you living, Ashman? Are you living in Manhattan?
No, I live in Jamaica, Queens.
Okay, it's very pretty there.
Thank you.
Yeah, I guess they want the first year students to make it alive into the second year. Beyond that, they evidently don't care.
They want the upper level students to live also.
Okay, everybody. Enjoy the fall weather.
Be well, everyone.
Yeah.
Thank you, Mel. Be well.
Yeah, thank
Bye.
you, David. Bye. Hagsamak. Bye-bye.
Thank
you. Don't
Bye
let
bye.
anybody cough on you.
Ciao.